بسم الله الحمد لله والصلاة والسلام على رسول الله. Okay, great. طيب, we will continue fuzzy logic. We have discussed the structure of the fuzzy logic system. You have fuzzification and inference. You have here fuzzification, and you have here inference or if-then rule we need to calculate. And then we have defuzzification. So at the end we have here a crisp value and the input here. These are some kind of measurement in your plant if you want to design a controller. So these are some measurements, numerical values. You fuzzify it, you convert it to linguistic values, and you measure the degree of membership. And you have here if-then rules, you calculate them, and then you have here linguistic value of the output. And you convert the linguistic output here to a numerical value, which is the defuzzification process. So we will see, and we discussed also the fuzzy sets and also the crisp sets, and we highlighted the difference between fuzzy sets and the crisp sets, and also the operators that can be implemented on fuzzy sets and or and not. And we know that an or means the maximum and means the minimum. So let us see how to calculate here, how to proceed in this, and how to evaluate the if-then rule. So this is the typical structure of the if-then rule. You have here antecedent and you have consequent. At the beginning, you calculate the antecedent based on your measurements, and the degree of satisfaction here is the same as the degree of satisfaction here. So if you calculate this, this also will be at the same degree of satisfaction, and then you will defuzzify it. So let us see, for example, one rule: if motor speed is slow, then we have voltage increases high. So we have here, this is the linguistic variable, speed, and its value is slow, and the consequence part is voltage increases high. This is the action part. So you have here high increase or voltage increase. You can have two linguistic variables here in the antecedent part. If you measure the speed and you measure also the acceleration, so you can say if the motor speed is slow and the acceleration is high, probably you don't need to do any action. If the speed is slow, but the acceleration is high, hopefully the acceleration is high means the speed will grow up. So that means you may not take any action here, or the voltage increase is low. So as you can see here, the if-then rules comes from the experience of the operator. This is what we have learned in motor, and we can easily develop such rules here based on our experience with the motor and the inputs and how to control the speed. So here this is the antecedent part. Look here, we have and. So this and means when we calculate this, when we measure the degree of membership of any value of the speed and how much it is slow, the degree of membership or the membership function value equal to 0.5, and when we measure the acceleration is high, we found it equal to 0.3, the membership value, and probably this is slow. this is the slope, and this is the acceleration is high. You measure the speed. You found the speed is here, so the degree of membership is 0.5 مثلا. And when you measure the acceleration, طبعا this is high. Of course, you have low and you have medium, and also you have here medium, and you have and so on. So this is the this is one rule. When the speed is slow and the degree of membership is 0.5. When the acceleration is high, and you can see here the degree of membership is for high is 0.3 مثلا, as we have here. So in this case, and we have and here. And means what? And means you get the minimum. You have here 0.5, you have here 0.3. So the degree of satisfaction for this antecedent part becomes the minimum of 0.5 and 0.3. So it becomes 0.3. So if this is 0.3, if this also will be satisfied by a degree of membership or a degree of satisfaction equal to 0.3. As we mentioned here probably last class, interpreting Evening rule involves two steps. You evaluate the antecedent, falsifying the inputs. You measure the input and you measure the degree of membership here, and then you apply fuzzy operators. This is fuzzy operators here, a, and, or. Application of the result to the consequent. And you have here 0.3, so this 0.3 is the degree of satisfaction of the voltage increase is low. Maybe voltage increase also has some values, low, high, and so on. So this is low, and this is medium, and this is high. So when you see this equal to 0.3, so this is 0.3, low with 0.3. So this is the output of this rule. This is the output of this rule. So this is the output of this rule. But this way, this is the output of this rule. So this is the output, or this is the consequent part. So the rule is if B is true, then Q is also true. If B is satisfied by 0.5, then Q also satisfied by 0.5. So when you measure the antecedent here with 0.3, so the consequence also will be satisfied by 0.3. So interpreting Evening rules is a three-part process. The first part is to falsify the inputs, as we have here. We measure the speed and then we convert it to 0.5. We measure the acceleration and we convert it to 0.3 for this degree of membership. So this is the first part. Second part, or second step, let us say, second step is to apply this operator. Is it and or minimum or maximum or not operator? And then you can, third step is to calculate the consequent accordingly. So falsifying inputs, resolve all fuzzy statements in the antecedent to a degree of membership between 0 and 1. So back to the example of the restaurant. If the service, assume that this is the rule, one of the rules that we implemented here. If the service is excellent, if the service is excellent, or we have here or, and the food is or the food is delicious, then tip is generous. Assume that the tip مثلا ranges between 5 to 25% of your bill. So generous means you are, of course, you can divide this to low between 5 and 10, and you can have some membership functions as such. you can range between, this is 5%, which is very low, and this is 25%. So you can divide this universe of the scores over this membership functions. So if the service is excellent or food is delicious, then the tip is generous. So this is the output. Assume that of course you have here range between 0 and 10. You assume that the surface has this value, which is very far from excellent. So the degree of membership here is 0. This is only the excellent, but of course excellent or good, مثلا you have other values here, and this surface is variable. This surface has several values, maybe excellent, very good, good, poor, fair, and so on. So you can assume that we have, for example, three values, either poor or good or excellent. So this is the excellent membership. So this is the degree, or this is the value, or your evaluation for the surface. Your evaluation here is like 2 out of 10. So in terms of excellent, this becomes 0. This is 0. Okay. And you give delicious masala, for example, 7 out of 10. So this 7, then it becomes like 0.7 of degree of membership of this. So you have this value equal to 0. You have this part equal to 0.7, and you have OR here. So OR means maximum of either 0 and 0.7. So the output of this becomes 0.7, maximum of 0 and 0.7. So this is 0.7. So the antecedent part is satisfied by a degree of 0.7. So that means also tip is generous. Generous is here. So this will also be satisfied by 0.7. Come on, this is 1. 0.7 is here. So you have it here. So this is the degree of satisfaction of this. So this is the shape of the output. How to exactly find the tip that you want to give? In this case, we will see the defuzzification, how to convert this area to a specific number here, which is the output of this. This is the defuzzification step that we will discuss in a few minutes. But this is how to calculate the antecedent part, and you have here the operator OR, so it becomes 0.7. So apply fuzzy operator, which is OR in our case. Apply fuzzy logic operators and resolve the antecedent a single number between 0 and 1, which is the maximum of 0 and 0.7. So it becomes 0.7. This is the degree of support for the rule. Okay. So you have the 0 or 0.7. So you measure the maximum here for OR. So it becomes 0.7 here. So the consequent also will be satisfied by 0.7. If this is the apply the implication method, use the degree of support for the entire rule to shape the output fuzzy set. Assume that this is the generous. Of course, the tip also is the linguistic variable. It has several values, maybe generous, maybe low, maybe medium. You have several values here. But this rule is represent generous. So we show you here the membership function of the generous. So this is 0.7. This comes from the antecedent. So 0.7 here. So this will be the output of this rule. So this is the output of this rule. It's 0.7. So we eliminate above 0.7. The degree of satisfaction is 0.7. Later we will see how to convert this area or this shape to a certain value of the tip. Maybe 20%, maybe 22%, maybe. We will see this in defuzzification step. I hope things are clear. If you have any question, please don't hesitate to ask. Fuzzy inference process, as we mentioned here, fuzzy inference is the process of mapping from the given input to the output using fuzzy logic. Assuming back to the restaurant example, you have two inputs that you want to evaluate in order to get the tip, how much the tip. Your variables here are surface and food. Surface, you give evaluation between 0 and 10, and then we fuzzify, and then we calculate the rules, and then we defuzzify later. So and the food also, quality of the food, is it delicious, is it poor, and so on. Assume that these are the rules. Okay. The first rule is this: if the surface is poor or food is rancid, then the tip is cheap. Okay. Second rule is if the surface is good, regardless the food quality, then the tip is average. If the surface is excellent or the food is delicious, then the tip is generous. So these are the rules that you have for the restaurant example. So let us see if you evaluate the surface, for example, at a certain value, like 3 out of 10, or you give it 4 out of 10, and for the input also give it a numerical value here. How to proceed from these numerical values, and you calculate the antecedent of this rule, and you calculate also the consequent of this rule. You calculate the antecedent of this rule based on these inputs, and you also calculate the consequent. You calculate the antecedent and the consequent, and then you sum them up, and then you end up with the exact tip that you will get. So the process here is the inputs are crisp between 0 and 10. Between 0 and 10. Numbers limited to a specific range. This is the evaluation. Second step is to fuzzify them. All rules are evaluated in parallel using fuzzy reasoning. This is the second step. The third step is to the results of the rules are combined and distilled or defuzzified, and at the end you get the output, which is the numerical value, non-fuzzy, crisp value here for the output. So let us see how to proceed with a certain evaluation of the surface and the food. Okay, before this, we need to point out here, we have two methods for defuzzification. Okay, so for defuzzification, we have two methods. You have Mamdani type or Sugino type. This method is used to defuzzify, convert from linguistic variables here or linguistic values to a numerical value. So we will discuss these two methods in details later. There are two types of fuzzy inference systems according to the way the outputs are determined. The first one is Mamdani type. This is in recognition to Ibrahim Mamdani. The output membership functions are fuzzy sets also. Typical rule is such. So you have the input here are fuzzy inputs, and also the output is fuzzy. And the output variable here is also fuzzy variable. So, and this is what we discussed so far. This is what we mentioned here in this example, مثلا. So the tip is cheap, the tip is generous. So the output also here is fuzzy. In Sugino, you have something else. You have, if the surface is poor and the food is rancid, for example, then the tip is calculated numerically as A times X. Assume that the surface is X plus B times the second variable, which is food quality. You give it 3, you give it out of 10, 3 out of 10, 4 out of 10, plus, just to have it, and you can have it in just a straight or linear equation. The output here, the tip here, or the output is just numerical values. So this is the Sugino type. This is the Sugino type, where you have the output as numerical expression from the inputs. We will see this in details later on. But what we are discussed so far is Mamdani type. This Mamdani type, you have inputs are fuzzy variables, and also the output is a fuzzy variable. So you have some linguistic values. Sugino type is the output membership functions are either linear or constant. Typical rules, if X is A1 is similar to this, and Y is B1 similar here, and the difference is here. So the output is not like this. It is not a fuzzy or linguistic value here, but numerical value, Z equal to B1, which is a constant, multiplied by X, and the Q1, which is the constant also, multiplied by Y, and you have constant here also, R1. Or you can have it Z equal to R1, and that's all. And you can have it constant, either linear or constant value. And you can have these coefficients equal to 0. So this could be done. So this is the Sugino type. Mamdani's fuzzy inference method is the most commonly seen fuzzy methodology, as we discussed so far. Mamdani's method was among the first control system built in the fuzzy set theory. It was proposed in 1975 by Ibrahim Mamdani, and as an attempt to control steam engine and the boiler combination by synthesizing the set of linguistic control rules obtained from experienced human operators, similar to what we have in the if-then rules of the motor. And you have some, the output is fuzzy also. The voltage increases high or voltage increases low. So this is the output variable. Mamdani type inference expects the output membership functions to be fuzzy sets. After aggregating the process, there is a fuzzy set for each output variable that needs to be defuzzified. We will see how to do it. Here, for this example of the restaurant again, assume that you have surface and you have 3 values for the surface: poor, good, and excellent. And actually, we divide here the values just for explanation. And you can have the the membership function of the good here, and then the excellent there. But we divide them as such in order to make it more and more clear. So if you are given, this is the for the surface, and this is the also for the food quality. We have two values here, rancid and delicious. We don't have any value here for this third rule. And assume that you give the surface 3 out of 10 and the food 8 out of 10. So 3 out of 10, so we are here. So this value is, for example, 0.2 or whatever. And the degree of membership here is 0.7 or 0.8. And the degree of membership here is 0. Okay, so these are the three rules that we have. For 8, this is 8. So in terms of the rancid, the membership is 0. In terms of the delicious, the membership value is 0.8 or something like this. So this is the first part of the antecedent, and this is the second part of the antecedent. And we have OR here. So this becomes 0.2 masalan, and this is 0. So the output here is, if you have OR, you have the maximum value between 0.2 and 0. So 0.2 and 0 is 0.2. And if this is the output, if this is the tip is cheap, this is the rule here. Tip is cheap, and this is the membership function of the cheap. So this membership function or this cheap will be satisfied by the same here of the antecedent. Now we said maximum 0.2 and 0. This is 0.2, for example, and this is 0. So the output here is 0.2. So this is 0.2. So this is the degree of satisfaction of the cheap. So this is the first rule. Second rule, this is 0.7, regardless here. So this is 0.7 will go here directly. So, and this is the average. Second rule is the surface is good. This is the degree of membership. The tip is average, and the satisfaction is 0.7. So we will cut here for 0.7. So this is the second rule calculation. The third rule, excellent, which is 0. You have OR here. The food is delicious. This is 0.8, for example. So OR is maximum 0.8 and 0. So it becomes 0.8. So this is the generous membership function. So we will cut it here at 0.8. And we will combine the whole output. The three rules here are fired. The three rules are fired. This by 0.2, this by 0.7, and this by 0.8. So we will combine them together. So we have the summation. So it's similar to what we have here. This is the shape that we have. Now, this is the result of all the three if-then rules. The question now is how to convert this output to a specific value or numerical value of the tip, which ranges between 5 and probably 30 is here, or 30, okay, between 5 and 30. So this is the range. You have different, defalsification techniques or methods in order to specify how much the tip that I will give here. This value or this value or 28 or 29, 25, 15, and so on. Any question? Okay. We have one. Okay, Hisham?
Doctor, I have a question.
Yes.
Why once the surface is excellent, we give it a 0 value?
Which one? Here?
Yes.
أنا 3 out of 10. يعني أنت الرينج this is 0 to 10. Okay? This one from 0, for example, this is 4. And this one starts from مثلا 2 to 8. And this one starts from مثلا 6 to 10. And did you get the point? And here, no, and actually here, we can write the surface. This is the membership function of the surface. You have bore, you have average or good, and then you have excellent, right?
Yes.
Clear. This is the surface, and this is ranges between 0 and 10, and you have here numerical value between 0 and 10. Am I right?
Yes.
Right now, you give the surface 3 out of 10. This is your measurements, and if you are talking about control system or a plant, this is the measurement of the speed, of acceleration, pressure, temperature, and you give the surface 3 out of 10. Okay, so surface is 3. So surface is 3. That means you are here. Sorry, this is the surface 3. So this is 3. So this 3 means that surface is this is good, this is poor, and this is excellent. Okay, so 3 for excellent, membership value equal to 0. This is excellent. Did you get the point?
And this we give the 3 now by a random number?
No. This is your evaluation. This is your evaluation to the surface. 3 is not a random number. Okay, and you are in the restaurant, right? And you said, okay, I will evaluate the surface and the food quality, and I will give the tip based on this. And you evaluate the surface at 3 out of 10. You give the surface 3 out of 10. Okay? And you give your evaluation to the food is 8 out of 10. So 3 out of 10 belongs to poor with 0.2 membership, 0.7 with good, and 0 with excellent membership value. Did you get the point, Hisham?
Yeah, I get the point, but if I want to compare it to something is logic, usually the excellent will have higher value than good, but I don't know why.
But you give a surface 3 out of 10. يعني you give a surface 3 out of 10. معناها انه السيرفيس is not excellent. معناها ان السيرفيس is not excellent. يعني لما تجيب when you evaluate something and you give it 3 out of 10, can you say انها excellent? Can you say ان 3 دي excellent evaluation?
No, but this is evaluation or as a weight?
No, not the weight. This is your evaluation for the surface.
Okay.
This is your evaluation for the surface. I give you a questionnaire and then you evaluate out of 10. You evaluate surface equal to 3. You evaluate the food quality 8 out of 10 and 3 out of 10. If you give it 3 out of 10, that means in the surfaces wasn't excellent, was not excellent. Is it clear?
Yeah, now it's clear. Thank you.
The surface is poor, actually poor, or somehow good. It's between. So this 0.2 and this is 0.7 here and 0 here. And when you give the food quality 8 out of 10, that means it's delicious. right? And you give it a higher evaluation here. So it is delicious. So the degree of membership of delicious equal to 0.8 and rancid equal to 0. Okay? The value of 8 here with respect to rancid, membership equal to 0. So you come up with this 0.2 and this is 0 and this is OR. So you get the maximum. So the maximum here of this antecedent part of the first rule is 0.2. If the antecedent is satisfied by 0.2, the consequent also will be satisfied by 0.2. Tib is cheap here. This is the fuzzy, this is the first rule. The tib is cheap and this is the cheap membership function. It will be satisfied by 0.2. So we will cut it here at 0.2. So this is the first rule output. Second rule, it was 0.7 regardless. So it's 0.7 and this is the average. This is the average membership. So it's satisfied by 0.7. So this is 0.7. So this is 0.7. For the third rule, this is 0 and this 0.8, so it becomes 0.8. So this is the generous. And this is the membership of generous, so it will be satisfied by 0.8, so it will be clipped here. So this is the output of the third rule. So you have 3 rules are fired here based on these inputs. You have 3 rules fired, and these are the outputs of the 3 rules, and you add them up, and this is the total output. This is the aggregated output. Right? The next step is to find, okay, this is the aggregated output, but how much exactly I will give the tip. So this is the defuzzification step. Nasser, Khalid, Sulaiman? Khalid.
Yes, Doctor, thank you.
Yes.
I just want to ask about the rules. They are left to the discretion of the system operator, or we
Yes.
have to take all the combination?
Of course, you can, if you have experience with the with your plant or your problem, you can develop the rules, if the rules. Okay, as you can have here, you have only 3 rules. Although, مثلا, for example, you have poor, good, and excellent here. You have 3 linguistic values. For the first, the surface, you have 3 values. For the food, you have 2 values, either rancid or delicious. So for the food, you have 2 values. Okay?
Yes.
So how many rules that we can develop? How many rules? These are the inputs, and each input has, one has 3 values and the other has 2 values. So how many rules that we can develop with all combination? Khalid.
If we are considering or only, I think it will be 6 here.
6 rules, yes. You can
Yes,
develop
but
here.
we are considering also and, it will be 12. 6 for or, 6 for and.
لا ما انت ما تقدرش تقول and or at the same time.
Okay.
And you cannot
So it will
say
be 6.
you cannot say no, one rule is surface is poor or food is rancid, then tip is cheap, and then you have another rule which is surface is poor and the food is and so on. So you can have here 6 combinations. Okay? 6
Okay.
combinations. Maximum I have 6 combinations here between surface and the food. But maybe based on your experience, based on your familiarity with the problem, you can say no, I can reduce this to 2-3 rules. مثلا, for example, this rule he said that no, if the service is good, regardless, yani the food quality, I will give directly the tip will be average. If the service is good, regardless, this is يعني based on your experience. يعني ممكن تقول مثلا يعني وعاوز يقول هنا مثلا في in this rule مثلا يعني بيقول لك المثل العربي يعني بيقول لك او المثل المصري يعني بيقول لك لاقيني ولا تغديني، مش كده؟
صحيح.
فهو السيرفيس يعني كويس، المقابله كويسه وكل حاجه، بس وات ايفر the surface I will give you an average tip. فيعني this is based on your experience actually. انما if you want to consider all the combination you have 6 rules and you can do the same for all. Probably for this example you can have as we mentioned here 3 rules are fire. The 3 rules are fired here. مش كده ولا ايه؟ We have an output for this, we have an output for this, we have an output for this. Maybe if you have more rules, sometimes you can have 0 or 0. In this case, the output will be 0 for the antecedent, and that means that this rule is not fired.
Yes.
Okay? So whatever the rules fired here, you combine the outputs. So this is the collective output of these if-then rules. The question now is how to convert this to a numerical value between 5 and 30. This is what we address here in defuzzification. I hope things are clear.
Yes, Dr. They are. Thank you.
The input of the defuzzification process is the aggregated output of fuzzy set, and the output is a single number. So we convert from the output fuzzy set to a single number here in the output. There are some widely used defuzzification methods. One of them is maximum membership, and we will see how. Mean of maximum, this is another straightforward calculation of the converting from fuzzy to non-fuzzy. Weighted average, this is another method. And centroid, you can get the center of area, and this center of area will give you a single number, which is the output of the defuzzification step. So the most popular defuzzification method is the centroid calculation. You calculate the centroid of this area, which returns the center of area under the curve as shown. And this is an area. This is the collective output of the rules, right? This is the collective output of the rules. Am I right?
Yes.
So can you calculate the area here and the center of the area? And you can say, no, this one divide the area here equal to the area here. This is the center. Center will lie on this line. So if this is the centroid, your tip is here. This is your tip between 5 and 30%. So you calculate the centroid. This area can be calculated easily. And then you can get the centroid, and then you have this value is the output of the process. So, but you can have also some straightforward values. You can have maximum of membership. We will see that mean of maximum, weighted average, and centroid, and then we will see how to calculate the centroid here. For maximum membership principle, this is very straightforward problem. If this is the collective output of the rules, one rule as such and the other as such, so this is the collective output. So you get the maximum here, this is the maximum, and you can see how much the corresponding here value. Okay. Okay, so this is the maximum. This is the maximum membership. You can have the value corresponding to maximum membership. This is the maximum membership, as you can see here in this shape. This is the collective. This is the aggregated outputs of all tired rules. Assume that you have it as such. So this method is simply you can have this value corresponding to the maximum membership. Is it clear? And probably مثلا the tip is 5 to 30 here. So this value may be like 12 مثلا, so 12%. So this is your output. So this is one way to convert from fuzzy to non-fuzzy. The other one is mean maximum membership. If you have, this is the collective output. For a certain rule, this is the first rule, this is the second rule, and so on. And you have, this is the collective output. So this method is simply addresses the value as the mean of the maximums. So you have the maximum here is A, and maximum here is occurred at B, so you get the average here of Z star, which is A plus B over 2. So you can get the average or the mean of maximum membership. So this is the maximum membership, and then you can have it. So maybe in other cases you can have مثلا this is the membership you have here and so on. So these are the maximum that you take. You have here A and B, and you get the average, which is the output here, Z star. So you can do this. The third defuzzification method is the weighted average. The weighted average method, this method is mostly used since it is one of the more computationally efficient. طبعا of course you can you can see that this is not the optimal way to calculate it. You are biased here somehow for the maximum. You can have several membership functions here, and then you pick this value only. But this will not give you a good estimate. The other one will be also still you have. But if you have such weighted average, it will give you a better approximation. So you have this one. This is the collective output of the rules that you have. طبعا this rule is if you complete it, is a combination as we have here. You have here, probably this part is embedded somewhere here. This part is, if you combine this with this, it doesn't show up here, right? So you can have such case, but this membership function has a symmetry or symmetrical. You have it value here, and also this one is symmetry or symmetrical around B. So this one is symmetrical around B, and this one is symmetrical around A. So this A, you have it membership value here is 0.5, and for B, the membership value here is 0.9. So you can get the weighted average here. You multiply A by 0.5, you multiply B by 0.9 over the summation, so you can get the weighted average. So you multiply the membership value, which is 0.5, multiplied by this value A, summation, so plus 0.9 times B, over the summation of the membership values, which is 0.5 plus 0.9. And the output will give you the weighted average of this. So you can have Z star, the output of the defuzzification step. طبعا انت you have A, I know this is known, will B is known also. So you can get Z star, which is the output value. طبعا this Z star will be a little bit biased with the higher or greater area here. Nasser, you have a question, Nasser?
Yes, Doctor.
Yes, please go ahead.
Here we are assuming let me ask again. If I want to make different ratio between the tip for the surface and for the quality of the taste of the food. So for example, I said if the surface is excellent, then is my tip is a 10%. If I'm talking to the extreme. If the taste is
wait. You said if. I'm writing just to comment on it. If surface is
excellent.
Excellent.
It means 10 out of 10. I'm giving a 30% of tip.
يبقى tip is 30%.
Yes.
Okay.
But and then I have another condition. The range is different. If the good of the taste is good, this is mean the food delicious. I'm giving 20%. So my range is different for this. This mean for me, I care more about, for example, the surface rather than the quality, or the opposite.
The tip is 20. But here, we have several comments here. When you say tip is 20% or tip is 30%, this is not a fuzzy. This is not a Mamdani type. This is Sugino type. Then you have a tip is fixed, 30%.
No, I still have combination between. For example, if the food is, for example, not 10, is mean, for example, it's not excellent, getting 8 out of 10, and then I have 27. And then if the taste is, for example, 8, and then I'm getting 18. So at the end, I'm getting 18 plus 28, look like around 46. This is what I mean. So at the end, I'm making combination between both, but everyone is different factor, a different importance to me.
Okay, no problem. You can do this, but let us agree on, and this is not a Mamdani type. This is Sugino type. Then the output here is fixed. The output here is not fuzzy. The output here is crisp value, 30% fixed, and this is 20% fixed, right? But how to defuzzify? This is what we will discuss later on. But just to address your question, you can say, okay, I will give the surface equal to 8 out of 10. So this is satisfied by 0.8. And this one is satisfied by 0.7, right?
Yes.
This 0.8 and the 0.7 are the weights. This 0.8 and the 0.7 here becomes the weight of 30 over and the weight of 20. Is it clear?
No, doctor, I'm not asking like this. What I mean, for example, if I get 0.8, it's mean 0.8 of the 30. It's not getting the 30 direct, so 0.8 is mean for me 24%.
This is when I say, and this is the weight of 30, معناها انه 0.8 times 30.
Okay. So it's not doesn't mean 0.8 is mean go directly to the 30 full.
لا ما 0.8 is a weight for 30.
Okay.
Plus this is 0.7. 0.7 is the weight of 20.
Yes.
Okay. Over summation of the weights here, 0.8 plus 0.7. So this is 24 plus this is
14.
15. So this is 38 over 1.5. So this is becomes like,
25.
25. So this is the combination here. But let us agree on, and this is the genotype. All what we have here is the genotype. Okay?
Okay, doctor, thank you.
Okay. إنما احنا we are addressing now for these methods Mamdani type. The output have a membership function as such, and this is the collective output of the you have here for this. For the maximum, or the mean of maximum, or the weighted average method, you have summation. Maximum here, or the average here is A, multiplied by this 0.9, 0.9, and so on, 0.5, 0.9. So the output is as such. Is it clear? Okay, the third method, which is more, accurate in estimation, is the centroid method. This procedure, also called the center of area, you are seeking for the centroid, or center of the area, or center of gravity, the most prevalent and physically appealing of all the classification methods. And this is widely used, although it takes some time in calculation, but this is in handy calculation. But usually, if you have, if you use fuzzy or MATLAB toolbox or fuzzy logic, then you can just call the such, or any method of the here. Assume that this is the collective output. This is the collective output. I want to find the centroid of this area, where this area is here is equal to the area here. So this centroid will give me the output value, the exact numerical value or crisp value here for the output. This Z is simply, or Z star here, equal to the integration of the membership values times Z dZ over the integration of the membership function over dZ. What does it mean? Integration means area under the curve. Integration means the area under the curve. So you have this curve, or this straight line. You can find this straight line as a function of the Z, as a function of Z. You can express it as a straight line equation here. If you know this value, for example, this comes between here, مثلا 3 and 0, and this is مثلا, for example, 1 here, so you have here مثلا 8 and 1. So you can get the straight line equation. You can have the straight line equation here. This is, and you multiply by Z, and you integrate from 3 to 8. You integrate from 3 to 8. And you have the straight line equation here, and you integrate from 8 to 10, مثلا. And this is the straight line equation, which is constant here, and you integrate from 10 to مثلا 15, and this is 18. You can get the straight line equation here, which is mu C of Z, and you integrate from 15 to 18 after multiplying by Z. And this is also the area under the curve. So dividing this, you can get the centroid, which is Z average here, or Z star. So let us take this example. This is the numerical example here for the declassification, using even mean of maximum, weighted average method, how much the output, centroid method, if you apply the centroid method here, how much the output. assuming that and we have three, this is a collective of three roles. This is the first role output between 0 and 5. Second role output, this is the membership function between, the scales here are, a little bit misleading, and this is between 0 and 5. This is between 3 and 7. It should be somewhere here, this is 1. And this is between 5 and 8. This is 1, this is 0.5, and this is 0.3. So this is the first rule output, and this is the second rule output, and this is the third rule output. If you collect these outputs, you will end up with this. So if this is the collective output, and you want to apply the defalsification method of mean of maximum method, what is the output? What is the Z that mean of the maximum? What do you think? Nasser Hakami. Do you have a question, Nasser? Or
No, still from the sorry.
Okay. So if you apply the first defalsification method, so the mean of the average, so mean of the maximum, so the output will come 6.5. Am I right?
Yes.
Yes.
This is 6.5. So this is the output. The weighted average method. The weighted average method, you have here this one. If it is completed, you can have it here. This is the combination. So where is the average here? Where is the average?
2.5.
2.5, and this is the weight is 0.3. So you have here 0.3 multiplied by 2.5 plus 3 and 7, so you are at 5. So this is the average, and the weight is 0.5. So plus 0.5 multiplied by 5. Are you following, ya shabab? Plus.
Yes, sir.
Yes.
Yes.
5, okay, 5 and 8, the average is
6.5.
6.5, and the weight is 1. So 1 multiplied by 6.5 over summation of the weights, which is 0.3 plus 0.5 plus 1. So you can calculate and you can see how much would it be. And you can have it. This is the mean of maximum, which is 6.5, and this is the weighted average, which is, as we mentioned, 2.5 and 5 and 6.5, and we multiply this 0.3, 0.5 times 5, 1.65 over the summation, so it gives you 5.41. So the output is 5.41 compared to 6.5 of the first defalsification method. Let us see the centroid method. Centroid method, you need to find out this straight line. Abdullah Yusuf, you have a question, Abdullah?
Yes. Can you go back? Can you go back? Excuse me.
Which one?
The weighted average method. How can we calculate it when the shape of the function is not symmetric?
Not symmetric, no. And if this is the condition, and as we mentioned here, probably for this one, unfortunately, do you see unfortunately here?
Yes.
It is usually restricted to symmetrical output. When you have the average clear here, this is the average clear. And now if you have unsymmetrical, so we are not going to the weighted average. So default, which one that can give you better results, smooth output, is the centroid that we will discuss now.
Okay, thank you.
So it is restricted for symmetrical output. Okay. So centroid, you need to find all the equation of these straight lines. And this one will be integrated between 0 and 1. This one will be integrated between 1 and the 3.5 or 4, whatever. And this between 3.5 to 4, and this will be between 4 and 5.5. And this equation will be integrated between 5.5 to 6, and between 6 and 7 you have this one, and between 7 and 8 you have the straight line here equation for this. So you implement this rule as follows. This is the equation of the straight line that you have here. This is, of course, passes through the origin, and the slope here is 0.3 over 1. So the slope is 0.3 over 1. So the function is 0.3 times z here. So this one is 0.3. This one, of course, you can have, this is 0.3. This point is 0.3, and no, not 0.3. This is equal to 3. For example, 6, مثلا 3.6 with 0.3, and this point is 4 and 0.5. Based on these 2 points, you can have the straight line equation, right? You can write the straight line equation here. This is equal to 0.5, and based on this point and that point, then you can you write the straight line equation and so on. So you can calculate this 0.3 z times z, z integration between 0 and 5, 0 and 1, 1 and 3.6. Line here is 0.3 multiplied by and so on. Between 0.365, this is the straight line equation. Between 4 and 5.5, this is the straight line equation, which is the horizontal here in this case. Between 5.5 to 6, this is the straight line equation. Between 6 and 7, the straight line here is 1, constant. So 1 multiplied by z is integration from 6 to 7. 7 to 8 over, this is the numerator. This is the numerator. And this is the denominator. Denominator is integration without the z. So this is the straight line here. This is 0.3 only. This is the equation of the line and so on. Of course, you can at the end you can calculate how much the z, if you divide the numerator of the denominator, and it gives you here 4.9. It gives you here 4.9. How much the weighted average?
0.41.
It is 5.41, and this is 6.5. Of course, the most the most accurate is the centroid, where you have balance between the. It is not biased in any way. So this is the centroid method. Okay, so we converted the collective output of the rules to a certain value, which is the output of the. So this is the input. You calculate it for all if-then rules, input 2, and then you combine with and or, and then you calculate the outputs. You collect the outputs together. You have the summation, and you end up with the with the collective output, and you calculate the centroid, and then this gives you the output. So this is the output. So this is the output that you have. So if this is the 5% tip, and this is the 30% tip, so you can see how much tip you will be here. Is it clear, Shabab?
Yes, Doctor.
So you do falsification first. You convert from a numerical value here, which is 3 out of 10 or 8 out of 10. You convert it to high and good and excellent and so on. And you apply fuzzy operator or and or not, whatever the operator here in the if then rule. And then you do the implication. The implication here is, if this is satisfied by 0.7, this will be satisfied by 0.7. This is the implication. The antecedent, if it is 0.5, then the consequent is 0.5. So this is the implication. And then you do aggregation. You aggregate all the output of the fired rules. And then you do defalsification using any method that you have here in the method, centroid or weighted average or whatever. Khalid Sulaiman?
Yes, if I have a feedback system, can I, after defalsification, I can take the out.
I couldn't hear you well, Khalid. Can you repeat your question?
Yes, Doctor. If I have back control system, can I feed the output again to the input after the defalsification?
The output to the
Yes.
input?
No, يعني if it's a feedback,
Yes,
I have to do defalsification. Then after that, it goes back.
Yes, you can say here, this is the blank that you have. Oh, this is the process.
Yes.
And this is the fuzzy logic controller. You do some measurements here. You measure the speed and acceleration. You measure pressure, temperature, whatever the quantities that you measure here. So you have some measurements, goes to fuzzy logic. And you have here the knowledge base. Knowledge base, if then rules, and you do the implication and you do falsification and so on. And at the end, you have the output, numerical value here, right? So this is the feedback that goes to the summing point here. If this is the reference, this is the reference value, masalan, and this is your action. You decrease it, if this is plus and minus. So the output here will go to the action. Output here is some kind of action. You decrease, you increase, but how much? This is the output here. Yes. You decrease it by 10%, you increase it by 5%. After defalsification, you will get 5%, 10% decrease, increase, and so on. So if you be reference equal, for example, 100, in this case, you increase it to this or decrease it to this, and so on. So this is the where the output will go.
Okay. That is very clear. Thank you, Doctor.
Genotype is we don't need the defalsification. لأن الأوتبوت is a numerical value. The output is not fuzzy variable that has linguistic values, but the output is numerical values. And the antecedent satisfaction will be the weights as we clarify in the example when we ask it about the 30% tip or 20% tip or another rule. The first two parts of the fuzzy inference process, fuzzifying the inputs and applying the fuzzy operator, are the same. The antecedent part is the same. The main difference is that the Sugeno output membership function are either linear or constant. and you can numerically calculate it. Typical rule of the Gini fuzzy model had the form: if input 1 is X and the input 2 is Y, then the output is A times X plus B times Y plus C. So I like a straight line here, linear. The output is linear combination of the inputs. You can have also the output is constant only. Z is C only constant. For a zero order, طبعا of course you can have A and B equal to 0, so you have only constant here. Each rule weights its output level. Yani the antecedent part here represents the weight of the output that you have. If you have 3 rules, rule 1, rule 2, rule 3, this is the output 0.3, this is 0.7, this is 0.2, and you have here Z1, you have here Z2, you have here Z3, the output of this, the output of this, based on the inputs, you can calculate the outputs. So this will represent the weight. So 0.3 times this, 0.7 times the numerical value here, 0.2 times the numerical value here, and then you can get the average later on. So the antecedent part represents the weight of the output. The final output of the system is the weighted average of all rule outputs computed as the final output equal to the summation of weights multiplied by Z over the summation of weights. Let us take a simple example. Operates as such. It operates as such. You have the inputs here, and you fuzzify the inputs. This input, degree of membership you calculate it, degree of membership you calculate it as usual, and then you have either and or. You calculate the antecedent part as usual. So this is the weight. And also you have X and Y numerical values. Go directly and you calculate the output, which is the linear combination of the inputs X and Y. A and B and C are constants. This is you set it maybe by trial and error, maybe by optimization. You can optimize, you can apply genetic algorithm or whatever optimization technique to find what is the optimal value of ABC when you want to design a fuzzy logic controller or a fuzzy logic system. So, but assume that you have A and B and C, these are constants. So whatever the measurements here, you can get the linear combination of this. And this is Z, and this is the weight. And then you can apply summation of weight times Z over summation of weight to get the output. So assume that Daima Nasser asked before, the first rule has a constant value. If this and this, then the tip is 10% or 5%. And the tip has a numerical value. This is the cheap. Cheap means 10%. مثلا. The second rule, average means عندي 15% or 20%. Fix it. And the the third rule here, tip is generous. Generous means 25%. مثلا. Or 30%. So when you calculate this, this is 0.2 and this is 0 here. So the output here is 0.2. So this represents the weight of this value, which is 10%. This is 0.7 regardless. So the output here is 0.7. So this is the weight of 15%, for example. This is what I define the average. 15%. يعني tip here is 15%. This means the average that I have here. Cheap here is 10%, for example. Generous is 25%, for example. So this is the 25% here value, fixed value. So this is 0, and this is 0.8. So this is 0.8 will be multiplied by the average of the value here is which is 25%. So you can do 0.2 times 10, plus 0.7 times 15 plus 0.8 times 25 over the summation of weights, then you can get the tip that you will pay. So this is the genotype, the fuzzy inference. Any question? Straightforward. Hisham.
Doctor, would you like to ask about the percentage of the 3 rows? Should the summation be 100?
Summation of what?
The tip percentage.
The tip percentage? What do you mean by tip percentage?
The first row we give it as a 10%. The second we give it as 15.
Okay.
The summation of the 3 should be 100?
لا انت actually range of the tip is 5 to 25%. This is your range of the tip. Okay? Is it clear? This is your range of the tip. But you have here 3 specific values. And you decide that low means I will, this is the minimum that I will pay, 10%. The average depends on the food and service and so on, I will pay 15%. And I may go to 25%. Depends on the service and food. So these are fixed values. It is not necessarily to have them equal to 20 or equal to 1. Okay? And that depends on the range. It depends on the range here that you define for the output. Assume that this is the motor example. Okay? The motor example, you have a voltage increase. You can set it. I will increase مثلا the voltage between 0 and 10 volt. If I have 3 rules as such, maybe 3 rules فقط, I can say no, voltage increase is 2 or 5 or 7 volt. This is low, this is medium, and this is high. This is my definition. Did you get the point, Sham?
Yes. Now it's clear.
It is not necessarily to have 100% here, and also not necessarily to have the weights summation equal to 1. This is not necessarily the case. Okay? Whatever you have here and whatever you decide here based on your experience, based on your familiarity with the problem, you can have the output here. The advantage of Sugeno is computationally efficient. مش محتاج السنترويد واللفة الكبيرة اللي احنا عملناها في الديفازيفيكيشن. You can easily have the numerical values of the input to calculate the output as a linear combination, and then you calculate only the weight of the antecedent, and then you have up directly the output. So it's computationally efficient, works well with linear techniques, and works well also in the optimization and the adaptive techniques. You can optimize the constants ABC. Has guaranteed continuity of the output surface. You don't have the discrepancy of the Mamdani, as we will see later in the advantage of the Mamdani of disadvantage of Mamdani. It is well suited for mathematical analysis. Mamdani is intuitive, somehow close to the human, intuition or human input. Well suited to human input when you use usually the linguistic values and linguistic variables. There is a MATLAB function to convert from Mamdani to Sugino or Sugino to Mamdani. So Mamdani system into a Sugino system will be a constant output. So you have constant output in the Sugino, so you can convert. If you have some rules in Mamdani type, you can convert it to this genotype. So you have some flexibility in this. There is some kind of type 2 fuzzy membership. I don't want to spend more time here. This is type 1. This is the membership function as we have. If you have any value here, you have a specific membership value. This is the type 1. Type 2 is you fuzzify the membership function itself. And you have the membership function. It is not a crisp value here as mu, but you have the membership function will give you the minimum value and the maximum value. So you have here the minimum value of the membership, and you have here the maximum value of the membership. So this is called the type 2. And you are fuzzifying the membership function itself. So it is not, have a crisp limit, but you have a fuzzy limit here. Okay, so you can degree, you can measure the minimum and the maximum here. How to implement the defuzzification? We will see later on, but let us take the question from Khalid Suleiman. Time is over, no?
Actually, I didn't mean to be rude. I just want to remind you it's over. And I apologize for interrupting you.
Allah, I didn't get, and I was looking to the watch. Now we started at 9, now it is 10:30. It's too much. So what is your question, Khalid?
No, I have a question. I just wanted to remind you that time is over.
Okay, so that's.
And sorry for interrupting you.
Okay, thank you very much. And I didn't see the notice or notification from Nasser until now. So sorry for being late. Okay, so this is what we have, and okay, let us continue next class, inshallah. Next class will be at 12 o'clock, right? Next class will be at 12 o'clock. And
can we arrange it to be a little bit early?
Can we keep it same 9?
No, it is not 9 now. I have a class starting from 5. Now it becomes 9. After that class, I am free. And we can have it earlier if nobody has a class.
I have a class, Professor.
Okay, so it will not work. If you want to shift it during the day, I have no problem. We can start at 4:30 p.m. up to مثلا 5:45. So
I don't think this is possible for me because we finish at 4.
If that's the case, Doctor, it's better to have.
It is just then one of our colleagues, he mentioned that his students, probably the students were full-time students. We shift the class 4:30. So, and I thought this could, but it is not applicable. So this option is not applicable. So we will keep it at 12. And after 1:15 means انه على السحور على طول ان شاء الله.
ان شاء الله دكتور.
Okay.
Thank you so much, Doctor.
Thank you. If you don't have any question, then you can stop recording, and we can. Any
Doctor?
question, ya Shabab? Yes, please.
Yes, I have question, but not related to fuzzy, related to the multi-objective.
Okay, go ahead.
For NSGA, we are doing generatic solutions, and then we are doing clustering many fronts, and then we are by this value between the fronts, and we are selecting the best parent and the offspring, and then we are combining the, for example, 50-50 or 100-100, and then we are coming back to the 100. If we do it in the beginning, in the population itself, and then we are moving all the point from the generic algorithm toward to the front. Is it okay like that?
يعني what do you want to say? And you have here you have the population B, right? This is the initial, and you select the parents here to form the new population U, and you do here, you select the population of the parents based on the fronts that classify here, and then you can do crossover and the mutation, and you have the new population. And in sequence, you will combine B and the Q. You are talking about NSGA2?
No, I'm talking about another way similar to this one. Maybe if I share, if you allow me to share.
Okay, share. Why not? Let me stop sharing from my side, and you can share.
Is it clear, Doctor?
Yes, I have it.
Yeah, if this is my functions, and then I for example, I have many points in the 50 point, for example, in the beginning, and then I got my Pareto by getting the non-dominated, and then I will use this, for example, 50 solutions, and then I will make for this 50 solutions offsprings, mutation, crossover, whatever, and then I bring another 50 solutions. And then I will compare solution 1 and this one with the solution 1. The one is nearest to the nearest to the, because I'm doing my minimization. So for example, if there is a 50 solution in the beginning, maybe I will get only 11 points, for example, in the Pareto set.
Okay.
So then I'm comparing, I will get another 50 solution, and then I start compare between this solution, for example, and this solutions. If it is much near to the origin from that one, it means it can go toward to the Pareto set, and then I increase the numbers. Rather than to go by ranking from the beginning, I am moving all the words. So somehow between the goal, what we call it in the beginning, the function of the try to remember, yeah, goal programming, and between the genetic algorithm.
Oh, يعني if I
because I have, yeah.
يعني أنت you have here 50. This is the first population.
Yes.
And then with the crossover and the mutation, and so you have a new population of 50 also.
Yes.
And you want to compare one by one.
Which I compare one by.
Which one is nearest to this?
Which one nearest to this? Yes.
Okay. So I assume that you have one is here, one to the right and one to the left of the line. So and this front here, one here and one here. So and you plot this red colors, but I want to shift. The one above the line is very near to the line, and this one is far from the line. So this one, of course, is much better than the solution in Pareto front, although the distance is high, or the distance is more than that one.
No, I'm not moving to the left, doctor. I'm moving to the corner, which is the shortest distance. As we said before, the shortest distance for the normalized function, it is the best for in case of minimizations. So I'm normalizing all the functions. I'm normalizing all the functions. Maybe I will just explain it again in a better way. For example, if this is doctor's my function 1, and then the solution is scattered hairs, but I still have another 2 solutions here, and then the offspring is here, and then for example I have a very good one is near to here, and then I have another 2 is here. So I'm comparing, for example, one from here randomly from one from here. If this one is they are nearest to the origin, I will take it. So if I compare this one, for example, with this one, I will take this one and then move it here. So this one will be cancelled, and I'm getting another point. So I'm crowding all my populations within the area of the front. So based on the nearest distance of the normalized function.
Yeah. Okay, in principle, it could be done. When you measure the distance between any solution and the origin.
Yes.
Okay. So this is gives you the distance, and you can have, but definitely, in two-dimensional example, you can see these figures here. But if you go to 3-dimension, 3 objectives or 4 objectives case, in this case, you may have 2 equal distances, but they are completely different from in terms of fronts. I don't know. Should I share and
Yes,
write
yes.
something?
Yes, doctor.
Okay. So assume that you have here
Are you sharing something?
did I share or not sharing?
No. Yes, not sharing.
Here?
Yes.
So you have it here. Assume this is the front.
Yes.
Okay. This point is non-dominated. Am I right?
Yes.
You may have a point here, which is very close to 0, and much better than this one in terms of the distance. But in terms of quality, this is non-dominated and this is dominated.
Okay.
Did you get the point?
Yes, I get the point.
So
if I keep
you assume implicitly you assume the Pareto front is very smooth as such, and this is not always the case. You can have this point as we have here, and this point as this is non-dominated and this is dominated. فالديستانس will not يعني give you a clear structure of the trade-off between the objectives, especially if you go to higher dimension.
So if I find a way, doctor, so that I am keeping all my previous point on the Pareto set, and then just I'm increasing the Pareto set, like what we did in the NSJ by doing the between the ranking, but I'm doing that one in the generic algorithm from the beginning, without doing multi-ranking, ranking 1, 2, 3, 4, 5, 6, 7. So I'm just enhancing my solutions during the generic algorithms, and I'm keeping the diversity by maintaining the old. If the point is already in the Pareto set, I should not replace it. I will give it its elitism.
Okay, no problem. You can do this. The technique is flexible, and if you have any idea that will help, but definitely you have to be careful as we mentioned here. And you need to think about it. For example, you mentioned in that example you have 50 in the population, and you create 50 solutions here with the crossover and the mutation. This one you have 11, as you mentioned, 11 solutions as a Pareto or non-dominated.
Yeah.
When you create the new population, you can test here also how many non-dominated solutions here. You may found 15 solutions are non-dominated. What you can do here is to combine
both.
So you have 26 solutions now. And with this 26 solutions, you can apply the dominance condition. And some of them will go out. And you have 11 solutions here. You may have 15 solutions as such. Okay?
Okay.
So in this case, these will be eliminated, and these also will be eliminated. So this is your Pareto front now. Am I right?
Yes, you're right.
So when you have 26 solutions here, and you apply dominance, you may end up with you eliminate some. You can have, for example,
13, 14.
Yeah, 13, 14 solutions. So
Okay.
this, keep them as an external set. This will be the external set. These will be the elite solutions. When you get another 50 solutions, you can get how much the non-dominated, and you combine with this, and then you end up with some of the solutions eliminated. And in each generation, you have to update your external set. Okay?
Yes, clear. Yes. Sorry, just to making it late for you. Yes, I have short questions regarding the best compromise method for you and UK. If I'm applying this method and I'm applying the short distance after getting the final Pareto set, will give me the same result at the end?
Yeah, most likely, yes. Most likely will be this the best compromise solution, which is the nearest to the, assuming that you are minimizing the two objectives.
Yeah, minimizing the two objectives, and then I want to compare the method, the short distance, and then the method of the finding the U1 and U2 and UK at the end, and maximize UK.
I think they will give you the same solution. They will give you the same solution. Try it. Okay. You can try it. If you
I will try. Just the question came to me now while discussing.
You can try it, and most likely it will be the same. But of course, when you calculate the distances, or when you calculate even the distances between the solutions, you have to normalize the objectives.
Yeah, it's always a normalization.
Yeah.
Okay, thank you, doctors. Sorry for making it.
No problem.
Thank you. Goodbye. Thank you.
Okay, Shabab, if you still have any question,